For this next section, we'll be demonstrating long-haul detection of changes in the Brillouin spectrum in a fiber. To help me out, I have Dr. Lufan Zhou, the developer of our Brillouin sensor system and our current technical manager. So, for long-haul detection, when light travels through the fiber, it attenuates over distance. A signal that starts off being 100 milliwatts at the beginning of a fiber, by the time it's traveled 50 kilometers, is weakened to be only 10 milliwatts. By the time it's traveled 100 kilometers, it is weakened to be only 1 milliwatt. So this weakening of the signal makes it harder to detect the Brillouin spectrum. To compensate for that, we have to work with longer pulse durations, which lowers the resolution. We also have to be using longer average times so that we can detect the signal from the background noise. In this demonstration, we'll be showing how to detect changes in the Brillouin spectrum over different distances in the total fiber length, illustrating how the resolution varies with distance. So to demonstrate long-haul detection, we have the following experimental setup. We have 6 different spools of fiber here, each one about 20 kilometers long, simulating a detection system over 120 kilometers of fiber. Later on, we'll be able to change the overall length by removing different reels of fiber. At the 60 kilometer mark, we've added a 10-meter length of fiber. Now this section is exposed so that we may change its temperature. This will change the Brillouin spectrum within the fiber, and we'll be able to sense that with our system. Alright. So, since we're starting off a new set of experiments, the very first thing we do is take a baseline reading. Every time you change your fiber or move to a different location, the first thing you have to do is take a baseline reading. This gets your initial readings from your fiber, and after this, all the measurements you take will show changes in the Brillouin spectrum compared to that initial reading. Now naturally this takes some time to do. Since we're doing 120 kilometers in this experiment, it naturally takes a little bit more time to make the baseline reading. But it's not too bad. We're working at about 1.5 minutes in total time to record the initial baseline reading. We have the instrument set up with the pulse duration set at 20 nanoseconds, which means that the resolution is 20 meters. We also have the averaging set at 3,000 averages, which is a reasonably number of averages for the measurements that we are taking here today. Currently we're about 75% of the way through our baseline measurement, and as we've noted before, once it's recorded all the data, the computer will then do an initial analysis and will show on the screen its initial measurements of the Brillouin spectrum. We're at the 92% point now. Just takes a little bit more data to read. We've gathered all of our initial data, and now it's doing the analysis calculation. And up comes our initial Brillouin spectrum. You can see each of the 20 kilometer spools on here. They're all slightly different because they're wound slightly different when they wind the spools. If we do the analysis and check the Brillouin spectrum, you can see that we have a spectrum here at the end of the 120 kilometer length, in the middle, and also at the beginning. And you can see it's quite strong there at the beginning of the fiber. Now we're ready to take our initial measurement. So for the purpose of this demonstration, we're just going to use the heat from Luthan's hand to warm the 10-meter length of fiber that we have out here exposed to show the measurement. So what we'll be measuring here is the actual heating that's being generated by his hand compared to the cool table underneath. Again, the section that we're dealing with is only about 10 meters long. So what we'll be seeing will be more or less an average temperature over a total of 20 meters over the region that we're heating. However, that is still enough to show you a real change in the temperature over that section. And we will be able to see a spike in our readout showing that temperature change. Right now we're at halfway through. We're about 47% of the way through the measurement process. What you see on the screen is the individual response at different frequencies as the system is measuring the entire spectrum. We're nearing the end of the process here. We're about 2/3 of the way through. Again, the purpose here is to actually detect that something has happened at that specific point in the fiber. That something has gone to change that Brillouin spectrum in that region. We're now 90% of the way through the data gathering. 95%. We have all the data, and now it's doing the analysis. Now if we zoom in to the region of interest, we'll see that there is a spike in the area that we heated the hand. As we said earlier, it's around about the 60 kilometer mark, and the temperature change is roughly 3 degrees compared to the initial baseline. And as you can see, it's well above the background noise variation in the rest of the fiber. Okay, now we're going to repeat our experiment, only this time we're only working with 100 kilometers of fiber. So once again, we're starting by taking a baseline measurement. Now this time we've reduced our pulse length from originally 200 nanoseconds now to only 80 nanoseconds. So that means for this measurement, instead of having 20 meter resolution, we'll have 8 meter resolution, which is slightly smaller than the length of the fiber that we'll be doing the test on, which is 10 meters. Okay? When you're doing actual measurements and you want to measure something precisely, you need the region that you're making the measurement to be longer than the distance covered by the pulse. That's why we're using 10 meters of fiber here with an 80 nanosecond pulse, which has a spatial resolution of 8 meters. The other thing we have done in terms of settings is we set our spatial step resolution to be only 2 meters. You want your spatial resolution to be higher than the resolution of your pulses. By having those two readings set properly, you're able to make good measurements with high resolution. We've just about finished taking our baseline reading. The computer will now do the calculation, and in about 20 seconds you will see the result. It's taking a little bit longer now to do the calculation than it did before, because we've made our spatial resolution tighter, now only 2 meters. So there's more data points over which to make the calculation. However, it is still less time than what it actually takes to gather the data. And in a moment, you'll see our baseline reading. So here again, you can see 1, 2, 3, 4, 5 sections of fiber in our measurement. And as we check, you can see that we have a Brillouin spectrum at the end of the fiber, near the 100 kilometer mark. And as we go along, you can see that variation in the spectrum here in the middle and at the beginning. Notice how the peak is getting larger as we go along. Now we're ready to take an actual measurement showing the real change in the temperature of the fiber. So once again, we're going to be using Luffan's Han as the heat source. So we start off our measurements again, and we start gathering the data. Now that we're working with 8-meter resolution instead of 20-meter resolution, we should see a much stronger change in the Brillouin spectrum, showing a higher spike for the temperature difference. And this should be much closer to the temperature difference between normal body temperature, which is 37 degrees, and the room temperature, which is around 20 degrees. The number will probably be slightly less since the person's outside hand temperature is slightly cooler. We're about halfway through the gathering of the data. And again, it takes about a minute and a half with our setup here. We are still using 3,000 samples for our averaging. So the data gathering is fairly consistent. Sorry, we're using 2,000 nanoseconds for our averaging. We're about 87% of the way through. (97). It's now starting the analysis. Okay, so it's no longer recording data, so we don't have to heat the fiber anymore. And again, it's taking about the same amount of time to do the calculation. So, only a small change, relatively small change in the length from 120 kilometers to 100 kilometers allowed us to tighten the pulse width from 200 nanoseconds to 80 nanoseconds in order to generate a good signal that the Brillouin sensor can measure. So this shows just how the relationships are between fiber length and sensing resolution. So the measurements are done, and if you look around the 60 kilometer mark, we do have a spike. And the temperature difference being shown right now is just over 10 degrees, which again, given that it's between a person's hand and a relatively cool table, is in line with our expectations. There we go. Okay. Now, for our final experiment that we're going to demonstrate, we've reduced our fiber length down to 80 kilometers, which will give us an even stronger signal for making measurements. So what is that going to allow us to do? Well, it's going to allow us to show you a new feature, which we call our fast measurement system. This fast measurement is very useful for things like fire detection in buildings, where you want to have a response much more quickly than the standard measurement system. Okay? So to begin with, we take a baseline measurement similar to what we do with our normal baseline measurement readings. We select, in this case, that the baseline measurement is for fast testing, and we start the measurement process. Again, we're going with 80 nanoseconds for our pulse width, 2 meters for our step size, and our averaging right now is set for 2,500. Okay, so this is similar to what we did before, but we're going to have a stronger Brillouin signal here, which is going to allow us to use this fast measurement system afterwards. Now, fast measurement isn't necessarily as accurate as normal measurement, but the trade-off is you get a response in a much shorter period of time. The initial baseline measurement that we takes as long as what normal baseline measurements take. You initially spend the time to get an accurate baseline reading. Once the instrument has spent the time to get this accurate baseline reading recorded, we save it. And we use that as our reference for all of our subsequent measurements. Okay? As long as we have a good baseline reading to begin with, our measurements compared to that baseline take place very quickly. This is the advantage of the fast measurement system. So here we are, we're getting our baseline reading. We're now about 64% of the way through. So you can see it does take roughly the same amount of time as before. We've taken about a minute so far, and as we had before, it takes about a minute and a half to take those readings. When we actually go to the fast measurement operation, you'll see just how much faster the whole system is. Not only measurement, but also analysis and generating a signal to say something has changed. So if speed is what you're mostly concerned with, the fast measurement technique will be very useful for you. So we're now almost collected all of the data, and now it's taking the time to do the analysis. Again, as I said earlier, the important thing is you get that take the time to get that good initial baseline reading. A good baseline reading is what makes this whole feature work well. About 56% of the way through the calculation. So 80% of the way through. Over 90% of the way through. And now it saves. So now we save this, and we save this file on our computer. Just give it a name. Once you have it and it's saved, we're now ready to use the fast measurement technique. You can see in our baseline reading, by the way, how we now have 4 reels, each one 20 kilometers long. And again, you can see now that we have quite a nice strong Brillouin spectrum, even at the 80 kilometer mark, and it just gets stronger there. So the fact that we're getting a much stronger Brillouin sensor is what's going to allow us to use the fast measurement. So we picked disaster warning, and this time we're going to pick fast measurement as opposed to dynamic measurement. So here's our initial setup. We choose temperature. Lufan put his hand there to start heating the fiber, and we start a measurement process. So right away, you can see that it's gathering data quite quickly. Okay, we're already 45% of the way through the measurement. To be honest, we're going to be measuring fast enough that we're going to be measuring faster than what the fiber can sometimes respond to in terms of the heat signal. We're already through the data gathering. We do the analysis. It's done. And if we zoom in onto the area of interest, we can see that we do have a spike, and it's showing a temperature change of 9 degrees, only slightly lower than what we did with our normal measurement system. So the combination of having a stronger Brillouin signal allowed us to use this fast measurement system, which allows you to measure temperature changes much more quickly than the regular measurement system. Now, just to show how fast this system is, we're going to start over and take two readings, one without the hand and one with the hand. So we're starting from the beginning again, using the baseline we already recorded. So we select disaster warning, fast measurement, and now we're going to load that baseline that we recorded. So we open it, we've loaded the baseline, we now select temperature, and we start making a measurement. So here we're taking the measurement without any heat source. So we're just going to see pretty much a flat line, and you'll see the noise in the signal. Fast measurement, again, is not as precise as regular measurement, but you get that advantage for speed. So if time is of the essence, and you're not trying to measure to better than the degree, then this works very well. You can see our signal here. The peak-to-peak noise level is on the order of 2 degrees. So now, that's our background. We're now going to take another measurement with Lufan's hand on the system. So again, we take the readings, and you can see again just how fast this whole measurement process is. Instead of taking over 2 minutes to gather the data and do the analysis, we are getting this done in a time frame of about 30 seconds. So this is much faster. And there you can see clearly the change in temperature occurring at the point where we are heating with our hand, well above the noise floor. So this just illustrates just how fast you can make measurements even over 80 kilometers of fiber and get good results.